Ron. Please give Ron a warm welcome. Crypto, you're doing it wrong. For guys that are standing on the outside, there are a whole bunch of chairs up front. Come over here and sit down, make some friends. You don't have to stand for the whole talk. You can come sit down. Most of the people at Shmoocon shower. This is not like Vegas. All right, I guess the rest of you want to stand the rest for the next hour. Anyway, come sit down. Make a friend. All right. With that, I'm actually going to hand it over to Ron, so good luck.
All right, thanks everyone. So, before this talk, I was at the bar at the hotel. Apparently, next door, there's a conference about pornography and voyeurism and stuff. So thank you so much for coming. Like, seriously. I thought of skipping. Like, microphone. Is it on? Closer to my mouth? Move it closer to your face. I hear that a lot. All right. So, let's get going. So my name obviously is Ron Bose. On Twitter, I'm YagoXA6. I have a blog, Skull Security. I work for Leviathan. We found a Skull Space, Winnipeg's first and only hackerspace. Apparently they're watching on the live stream right now, and they're taunting me from IRC, which I can't see, thankfully. And when I'm not doing computer stuff, I'm into rock climbing. Yes. I live on the prairies, so it's interesting. All right, so my agenda for today, I'm going to start by talking about the history of crypto attacks a little bit. I'm going to do some examples. I had a really ambitious talk planned out. It was about 3 hours long, so I cut out a bunch of stuff. I'm posting some slides to GitHub after. It's going to have a lot more slides than I actually present. It's going to have, I think, 2 more vulnerabilities and 1 more tool that I don't even talk about today. So make sure you check my slides after. There'll be a lot more. So I have three major types of attacks I'm going to talk about, and each of them I have a demo, and the demo is going to be live coded on stage. I arm my friend with a smooth ball. If I script a demo, he's throwing it at me. So they'll give you right the first time, I promise. But then I'm going to talk about some solutions, because when I don't talk about solutions, people get mad. So why am I doing this? This actually originated with a capture the flag contest I did a few months ago. It was Stripe CTF. There was a level in it where you had to implement a padding oracle attack, or sorry, not padding oracle, a hash extension attack, and it was tough. Like, I've spent like 6 hours till 8 o'clock in the morning working on this before I finally got it, and I decided to write a tool for it. And after writing that tool, I wanted to write more tools for some other attacks, like padding oracles and stuff like that, just for my personal interest to learn how they work. And then suddenly I had a bunch of tools and a bunch of cool, not new research, but stuff that people have done before, but that hasn't been presented really well that I could find. So I thought I'd do a talk about it, and here I am. So, history of crypto. So this is going to be a very brief history. It's not going to be very accurate, I promise. So it all started in 75 BC or so with Caesar. Caesar allegedly had what he called the Caesar cipher, a shift cipher. It had 25 possible encodings, 26 if you count A becomes A, which is a terrible encoding. Yeah, it's double ROT 13. It's secure. It's twice as secure as ROT 13. And I actually did, as research for this, I did a crypto quote, and it took me about 10 minutes. I took a video of it. I can show you the video if I run out of time, or if I have extra time. It's terrible. I won't show you it, I promise. But it's trivial to brute force. And this stuff you see on the screen, and all examples I give are all legitimate encoded stuff. You can verify it, you can look it up. I try to make it funny. The last part is LOL, in case you couldn't guess. So, after Caesar, there was a couple thousand years of developments and stuff like that. I decided to be really lazy and do the research, so I went to 4chan. And I asked on 4chan if anything happened in the interim between Caesar and Enigma, and they said no. So, as you can imagine, it was quite a time saver. All right, so Enigma. I promised my friend I'd put Hitler in the talk somewhere, so here he is. He's been Goodwind, Godwind, whatever. All right, so the Enigma machine was the first real crypto that I know of that was actually more difficult to break than just like making guesses until it worked. Um, to break Enigma, it actually relied on things called cribs. And if you guys want to learn a lot more about this, Wikipedia was great. I spent a whole day when I was supposed to be working reading Wikipedia. I also, the Cryptonomicon is an amazing book. They talk about this in great detail. Neil Stephenson, I highly recommend that book if you haven't read it. But anyway, the idea behind Enigma is that they had to break it at the time. They had to know certain keywords that were in messages. And if they could break a message for the day, any single message for a given day, they can break all the messages because of key reuse. So that was really cool. But how do you break one message? Well, they had to figure out some content that was in the message, and they had a lot of ways of doing this. I'll talk about 3, and then I'm going to move on to actual modern attacks. So one way, the Germans actually had a whole bunch of spies in the UK, and the UK knew about them because Enigma was broken. And at points during the war, MI5, the British intelligence, could say, we're 100% certain there are no unknown spies in the UK. Every spy is either arrested, deported, or working for us. And it was true, there was no German spies in the UK for long periods of the war. So the spies that were on the British side, the turncoats or whatever, they would send messages that had special keywords in it. And those messages would get repeated over the secure Enigma network. And those keywords could be found by the cryptanalysts, whatever, the smart people. And they would use those to decode the messages, and that would let them decode all the messages for the day. In the Cryptonomicon, they talk about this. They would plant mines at certain locations, and they knew how the Germans would encode the locations as coordinates and send them on Enigma. So they would find these coded strings, and then use those to decrypt that message, and therefore all the messages. Like, it's really cool. And a lot of this comes down to operator error, like the fact that the Germans should have known better than to like leave code books lying around in some cases, or to start every message with a current date, or things like that. But they didn't, and that let them be broken. So that's kind of where I'm going with this. So more modern, but it's not very modern. All right, so DES. So in the 1970s, we got DES, a symmetric key cipher. Basically, messages can be encrypted by a person and decrypted by anybody with a key, which is the recipient and everyone who's stolen it. So that's obviously a problem. Key management, right? It's always a problem. Which leads to asymmetric key encryption, Diffie-Hellman, RSA, stuff like that. For asymmetric encryption, both parties, Alice and Bob, have to exchange their keys with either each other or with Eve, and then they can communicate with each other through the untrusted third party. So again, this is a problem, implementation problem, which leads to CAs. I promised my friend I'd put Ghosty in my talk. That's the best I'm going to give him. Sorry, Mac. So basically, with CAs, you could try to verify certificates from people, and whichever CA was the most trustworthy, or was the least trustworthy, would be compromised and would verify anybody. There's lots of talks about bad CAs. I'm not going to talk about how bad they are. They're just, we all know they're bad. While we're talking about Ghosty, let's talk about WEP. So WEP uses RC4, it can be used securely still. It's very difficult to, but used with a 24-bit IV. And we're going to talk about IVs and how important they are later. But for the purpose of this, a 24-bit IV is totally worthless. You get a collision every 5,000 packets or so, which is, as soon as you have 2 packets with the same IV, you have a problem. So, RC4, an okay-ish cipher. How it was used, not so good. GitHub. So this is a story from a couple weeks ago that was actually pretty interesting. It kind of goes well with my talk because GitHub and GitHub is giving people, GitHub and SVN and stuff, they give people a great place to accidentally post keys and accidentally post passwords. And that happens a lot. Like, who here hasn't posted a password to GitHub by accident at one time or another? I know I have. So, what's the point of all this? Well, the point is that encryption is rarely broken directly anymore. Most of the algorithms we have, even things like SHA-1 and MD5, they're bad algorithms. They have a lot of attacks. But it's rare that you actually break something through directly attacking the algorithm. It's broken by bad implementations by developers, bad operations by end users, just stupidity like CAs, various side channel attacks, timing attacks. The Lucky 13 or whatever it is, vulnerability from last week, I think, was a timing side channel attack against against SSL and TLS. Like, we're not breaking the algorithms directly. We're breaking them through side channels, and that's kind of the point of this whole intro section, and the point of the next three examples I'm going to give. We're not going to break anything directly. We're going to break them by how they're implemented and how they're used incorrectly. So important concepts. So these are going to be very oversimplified because this is Shmoocon, and you all know what encryption means. So I don't need to go over this in detail. So encryption is the art of obscuring data with a secret key such that only the intended recipient and anybody else who's stolen his key can actually read it. That's encryption, right? Whoops. Block ciphers. We're going to talk about block cipher, attacking against block ciphers. Actually, two attacks against block ciphers. Basically, the idea is that you divide the plain text into blocks, you encrypt each block, and there you go. We'll talk about much more detail of that when we talk about padding oracles. There's different modes of operation. So ECB is electronic codebook. This is the simplest possible implementation of a block cipher. So you take a chunk of plain text, 8 bytes, 16 bytes, whatever. You encrypt it with a key, you get ciphertext. You take the next 16 bytes, you encrypt it, you get ciphertext. Any two blocks are the same, get encrypted the same. Any two blocks are different, are encrypted different. That's why you see in the corner here the picture of Tux. This is on Wikipedia. This is all over the place. A very common image about why ECB is bad. In the original image, the background is one color, the skin is black, the stomach is white, etc. Every single 8 bytes that are black get encrypted to the same other color. Every single one that's white gets encrypted to a different, but also the same as every other white color. So you wind up seeing these patterns, and you can see the overall shape. And that's why ECB is bad. And, I don't need to tell you this, but I did anyway. CBC. CBC is where it gets more interesting because every block gets encrypted differently no matter what. And there are some attacks, like padding oracles, that are specifically against CBC. And that's the attack that I talk about for this talk. And we'll talk about this in detail when I get there, so I'm not going to spoil the surprise. So IVs. The IV, or the initialization vector, is the input into a hash function. It's designed so that if you have the same data and the same key, you don't get the same ciphertext. If you do get the same ciphertext, it means you're giving the attacker some information. It means that you can see when two things are encrypted the same way. And we'll see very shortly why that's a problem. All right, hashing. We all know what hashing is. Taking lots of data, reducing it to a little bit of data. Easy. Anyway, let's get on with the good part, the attacks. All right, so the first attack is key reuse in block ciphers. There's about 10 or 15 skip slides here that I put a lot of work into about key reuse in stream ciphers. Please download my slides later and read it. It's actually really, I put a lot of work into it, but it was the least interesting of the attacks, so it got cut. So, key reuse. So, using the same key in IV to encrypt two messages is a fail. It can affect every single crypto algorithm, basically, because it's just the nature of how, it's just how data works. And we'll see why as I do this example. So this attack I'm going to show specifically works when a block or a stream cipher is used, although there's better ways to attack stream ciphers with key reuse. And the attacker needs to control at least a certain number of bytes, the block size in bytes. So we're going to use DES as an example. DES is a block size of 8 bytes. So the attacker needs to control 8 bytes at the beginning of the string. I should mention too the concept of an oracle, a crypto oracle. So in crypto terms, an oracle is some program or service or whatever that will perform a cryptographic operation on behalf of an attacker and give him some well-defined response. In this case, the oracle will encrypt data for the attacker with his own prefix and respond with the encrypted data. Anything after the prefix can be decrypted, and we'll see why. So here's our oracle. This is written in Ruby very quickly, very simply, as simply as I could. Basically, it's a function that performs a crypto operation. It creates a DES cipher. I'm only using DES here because it's easy to demonstrate and has short block sizes. This will work against everything. It'll work against AES in every mode. It'll work against stream, block ciphers, whatever. We're going to set the key to my DES key and return the encrypted version of the prefix that the attacker specifies, concatenated with, this is some test data. This is some test data is unknown to the attacker for this example. So if we call this function with 16 letter A's, this is more to demonstrate how ECB works than to actually show the attack. If we encrypted 16 A's, we see we have the plaintext 1 is all A's, plaintext 2 is all A's. The ciphertext 1 and 2 are also the same value, 7, 1, 3, 4, E1, etc. Because we have two blocks of the same, they encrypt the same value. That's ECB. That's what we're talking about. Now, if we encrypt 7 A's, what happens? So the attacker knows that the string is 7 A's and then one unknown character. We as the people watching this talk know that the unknown character is T. So the service will encrypt 7 A's and the letter T, and the value will be EA, CA, etc. C1 there. The rest of the string doesn't matter for this. Totally ignore it for now. So that's our goal, is to find something else that encrypts to EA, CA, 59, etc. So it's pretty trivial. It's only 1 byte of unknown data. So we just try every possible byte. That's 256 tries. We try 7 A's and A, 7 A's and B, 7 A's and C, etc., etc. Eventually we get to 7 A's and T, shown towards the bottom there. When we get 7 A's and a T, we get the same ciphertext, the same block, which means that we know now the first block was 7 A's and a T, and therefore we just decrypted the first byte. Then we encrypt 6 A's. 6 A's are encrypted, and then we know there's a T there. Next character, we don't know. As the people watching this, we know it's an H. The attacker doesn't know it. So now his goal is to find whatever encrypts to CB, 7A, 74, so on. So he does that by guessing, again, 7A's TA, 7A's TB, 7A's TC. Eventually he gets to 7A's TH. When he does, he gets the ciphertext in green at the bottom there. CB, 7A, 74, etc. That's the same thing we're looking for. So as an attacker, we now know that we have 6 A's and then TH. So we just decrypted 2 bytes. And I'm not going to go through every byte. I wrote a blog once where I did like an entire string of decryption by hand, and it's terrible. So I'll stop here. The point is we can do this over and over again until we eventually get the final result. So what's going on here? To explain it in a simple way, we are forcing the first unknown byte to always be in a block boundary. So we're forcing the first unknown byte to always be encrypted alone, which means we have a bunch of known bytes and an unknown byte. Guessing 1 byte, that's easy. Brute forcing a single byte is trivial. It takes seconds, milliseconds. And yeah, we can do that and guess the whole string. So I wrote a tool to do this. It's called Prefixer. Basically, it implements this attack in a generic way, and I'll do a demo. I'll show you. So let's do it. So before I do the demo, I will show you the server I wrote. This server is actually quite simple. I wrote it in Ruby. It's poorly written. I don't write Ruby servers usually, but it works. So for the key reuse attack, you basically can specify prefix, and it encrypts the prefix with whatever cipher you choose, DES, AES, or whatever, and it'll encrypt unknown data. So we can just play around and put like AA, 4141 is AA. Choose DES ECB, just again, because it's easier. You encrypt it, and the results of DES ECB, and encrypting 4141, the 2 bars means concatenation in crypto. So concatenate with text 1. So text 1 starts with S, skull spaces, blah, blah, blah. So that's a text we're going to try to brute force by using this technique. So we can see this works, and it's fairly straightforward. Now all we need to know for this is what the URL looks like to actually encrypt data. And that's what this is here. So I'm going to copy that and then give you a quick walkthrough of Prefixer. So Prefixer is sort of written in the modular way. The prefixer.rb itself, it's obviously a Ruby program. This is not the right folder. So the prefixer itself is a really simple Ruby script, but you don't need to actually use it. You basically write a module, and the module implements a way to send encrypted data to a server and get the result back. So I'm going to take demo.rb, which is a very simple demo that I wrote, and call it Shmoocon.rb. Live demos, gotta love them. Shmoocon.rb. It's a lot easier to type when there's not 1,000 people watching. All right, so we look at our demo. It's pretty straightforward. It includes HTTP party, which is an HTTP client. Yay! And all right, and then I'm glad someone likes it. And it includes Prefixer. So we're going to read in the module to Shmoocon. If I can type Shmoocon. Nope, I can't type. and call it Shmoocon here too. Shmoocon. So in initialize, we don't need to do anything. All we need to do is know how to actually encrypt the data, which is this, encrypt with prefix. So we're going to replace this test string here with what I just copied and change move data to over here. So now it's going to request localhost / key reuse question mark blah blah blah. This is syntax in Ruby for making a hex string. Originally I was doing this without making a hex string, and that just made everything not work. So now we need to extract the encrypted data from the page. So when you prepend 4141 to this and you hit submit, the encrypted data, thanks to the guy who wrote this, is actually between two sets of 3 square brackets. So that makes it really easy to extract. In theory, this is going to be a lot harder in real life, but this is Shmoocon, right? So let's do it. So we're going to take result.gsub. We're going to replace everything before the 3 square brackets with nothing. Then we do the same thing. Oh my god, I can't. How do I vim? Do the same thing for the closing brackets, dot star, and then return it. So in theory, this should strip out everything except for that string. There's better ways of doing this. There's much better ways of doing this, but who cares? Another thing you can do is specify a character set. So this is the characters I'll guess in this order. There's lots of places online where you can find the most common characters in English by just the characters, like A to Z. Sorry, I'm in the US. A to Z. Sorry. But it's really hard to find ones that include punctuation and capitals and stuff like that. What I wound up doing was just like, I need some source of data. So I went to Battlestar Galactica's wiki page. I downloaded the whole database, and this is the ordering from that database. Like, that's the best I could think of. All right. So that now down here, and this is optional. We don't even actually need this. Like, there's built-in lists. So now we create the new module. We call the module Shmoocon. So let's do that. CW Shmoocon. And then we do prefix.decrypt. We pass in the module. We pass in true. This true means that it's a block cipher and there's padding. And the last true means that it's going to be verbose. So we're going to save that, and we're going to run it and hope it works. If it doesn't, there are shmoocons ready, I'm sure. Oh, there we go. It works. Whew. Thank you, demo gods. Let's clap. All right. So that's demo 1. 1 down, 2 to go. That is not the right window. All right, so how do you prevent this? My one token sign on how to prevent these attacks. Use different and random IVs whenever you encrypt data. Simple as that. If possible, change keys. That's not always or usually possible. If you're in ECB mode, you can't defend against this, so just don't use ECB mode. For this and many, many other reasons. All right, hash extension attacks. This, as I said earlier, is what kind of got me into this. I captured the flag where this was an issue. The basic idea, and this, I'm doing these in order. The last one is the simplest one to understand. The next one is the hardest one. This hash extension is actually pretty easy. For those who don't know, hashes can pick up where they left off, and that's all there really is to it. We'll see what that means as we go. The setup. So this isn't so much an oracle like the previous one was, but this one has a very specific coding problem, and that's that an assumption is made by the developer that if you concatenate secret with some data and don't tell someone's secret, then they can't change the data. And that, it turns out, is not true. If the attacker doesn't know the secret, he can still add data to the data without actually knowing the secret and get a new invalid hash. We'll see why that is. So before we do that, let's look at how hashing actually works. So here's an example hash. This is the first paragraph from Call of Cthulhu because it made some really cool text. And it's actually fairly appropriate if you read the whole thing, but please don't listen to me instead. It's pretty small anyway, so maybe you can't. The point is, when you hash something, the first thing that happens is it's broken into blocks. The block size of hashes is actually a lot longer than the block size of ciphers. We were talking about ciphers earlier, which is 8 or 16 bytes. Hashes start at 64 bytes, 128 bytes, or more. So bytes, the block size is fairly large. So it's first broken into blocks, where every second, each, blocks work. Then padding is added. So the very last block is padded. It's padded with the 1 bit and a bunch of 0 bits and then the length. So the 1 bit in terms of bytes is 80, and then 00000000, etc., up to the full block length. And then the last 2 bytes of that padding are the size. It's the size in bits. That wasted me hours not knowing it was in bits. Also, pro tip, different ciphers use different endianness. So MD5 and ripe MD5, or ripe MD160 rather, use little endian for everything. SHA-1 and that family use big endian. When you're writing a tool for this, that confuses me. I wasted days on that. I tried using OpenSSL for reference, but that made things worse. This line here is about insanity. OpenSSL, that's a perfect line for OpenSSL. All right, so let's look at how the hashing sort of works. So the first block is hashed, and you get some, if you can't read this, it's not a big deal. The first block is hashed, and you get some output. That output for SHA-1 is 5 32-bit values. These values are the state or the context. With MD5, there's 4 32-bit values. With SHA-256, there's more. The point is, every block outputs a set of context. That context is eventually it gets to the end. The very last block outputs context, and that context is the hash. And that's what the key is, that the context is the hash, which means if you have the hash, you also have the context. If you have the context, you can make another block. So this, for example, you can add another block that says, hello, yes, this is dog, plus padding. And by only knowing the output of the original hash function, which was ed88 whatever, and by knowing the text we want to add, we can calculate the hash of the original potentially unknown text, concatenate with the padding, concatenate with our text. So that's pretty cool. That's an attack that people don't realize can happen. And when I first figured out this attack, I didn't really understand it. Like, me and 2 friends, Mac, who's mentioned on the slide, and Alex, who's right over there, we're sitting in a room together, and they're saying, like, hey, you can just add padding. You can just add to the text. And I'm like, you guys are crazy. It turns out I was crazy. So it's pretty cool. So let's take a look at a real-world example. There's a site called Flickr you may have heard of. It's pretty popular. Yahoo owns it now. And they had a vulnerability many, many years ago in their API. The way their API worked was the client and the server would share a secret. This secret was some long hex value or something. When you want to send a command, for example, like add a picture or delete your account or whatever, it would concatenate that shared secret to the front of your commands and take a SHA-1 of it. And then that SHA-1 is prepended to the commands. When the server received this, it would calculate the SHA-1 with its copy of the shared secret and with the commands that you sent. If it matched, it assumed that you were legit and let you access. So that was a real vulnerability. Now, to simplify things, let's look at a fake server. So I put commands, for example, can be like set first name equals Ron, set last name equals Bose, delete my account equals 1. Just simple commands like that. So how would this actually look in real life? So message would be the SHA-1 of secret key. I'm literally using the word secret key for the secret key. It's like using password. No one would ever guess it. That first person who used password for his password was brilliant. I'm just going to say that now. So he calculates a hash. The hash happens to be 5E8A88, blah, blah, blah. He concatenates that with his message, and then he sends that. Now he sends that to Flickr, and Eve captures this. And then what can Eve do with it? Well, Eve now has a message and the hash. Now remember that this hash is the SHA-1 of secret key concatenated with the command. Now Eve doesn't know secret key, but Eve does know the command. So Eve knows that the command was calculated by taking the MD5 of set first name equals Ron, and then the 1 bit and 0 bits, so 800000, and the length. Now the length is a tougher one because without knowing the secret key's length, Eve wouldn't know what the length would be. But it's brute forcing, right? How long can the key be? So Eve knows that would output that value. Now because Eve knows what the state is at the end of this, Eve can then generate her own state, which is, for example, ampersand delete my account equals 1. So Eve starts with a state of the 5A whatever, and then add delete my count equals 1 to it, and it ends up with the new state. Let's see how that can be done. So this is, I actually wrote this code. It took me way too long to write this. But basically, you initialize SHA-1. You then take the context and set the 5 values in the context to the 5 output values. And this is really dark, I apologize, but it's okay. You set the 5 context values to the 5 values that Eve knows that she saw from the packet capture. And then she calls SHA-1 final, or rather SHA-1 update with her new data and a SHA-1 final. She compiles that, she runs it, and it gives her B8, 41, etc. So she then sends B8, 41, etc., which is her new hash. And then she sends set first name equals Ron, the original message. Then she sends 80000000, whatever, the padding. And then she sends and delete my count equals 1, the new data. The server receives this, and this text at the bottom here is calculating the digest. The digest of secret key, set first name equals Ron, blah, 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 is the same thing, B841, because it's the same thing calculated a different way, which is really cool that you can do that. Now this is really hard to do by hand. Like I said, it took me about 6 hours the first time because you're dealing with endianness, you're dealing with bits, you have to get the padding just right. It turns out I can't count, I can't add, I can't do anything. It's really hard. So of course I wrote a tool for it. Now this tool is written in C, which let me use the OpenSSL library really easily. And I supported all the hashes I could find. MD4, MD5, RIPE MD160, SHA, SHA1, SHA256, blah, 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 Whirlpool. I do not support SHA-224 or SHA-384. The reason for that is those are actually truncated. So SHA-224 is actually SHA-256, missing some context. SHA-384 is actually SHA-512, missing even more context. So those are actually slightly more secure than their counterparts because they're missing context. SHA-3 is by design, should not be vulnerable to this. I have never checked this. I am not an actual cryptographer, despite what I'm here talking about. I apologize if I led you astray. The most complicated thing I do is exclusive OR, but it turns out that's enough. So SHA-3 is designed to not be vulnerable to this. Now, I'm not going to talk about this slide because I'm just going to do it for you. Let's look at cats. Thank you. All right. I like cats. All right. Just because I like punishment, I gotta make and everything. Please compile, please compile, please. Yes. All right. Now, let us look at the hash length extension. So this is pretty much the example I was talking about earlier. You're given a signature and some data. So your data happens to be action equals read file, and file equals something boring. The signature of that, when the secret that we don't know is preprinted to it, turns out to be 0A, E2, etc. So it tells you here that secret length is 14, just laziness, and the signature is calculated as secret concatenated to action equals whatever. So your mission is to append a different file name and also make a valid signature. So I put a box for the signature, and I put a box for the data. So if we want to verify this is working, we can take the original signature and the original data. And this will obviously work because, in theory, this signature is for this data. So we paste in there, we hit submit, and it's success. So the original stuff works. Makes sense. If we change the signature in some way, or sorry, if we change the data in some way, so add, for example, file equals dot slash, that's not dots at all, dot slash, whatever. That's, oh my God, how do I computer? If we try doing that, it's going to say failure because we just gave it a bad signature. So now, let's generate a good signature for this. So that's where this tool comes in. So the tool is called hash extender, and it takes a whole bunch of different arguments if you want. The format of the output, the format of the input, et cetera, et cetera, et cetera. Lots of good stuff. The 5 main ones are at the bottom here. The data, the original signature, what we want to append, the hash format, which is MD5 in this case, and the length of the secret. So let's do that. Hash extender -d data. So the original data we have here is this. So copy, paste. That's original data. Our signature is here. what we want append, let's append file equals dot dot slash etc slash password. The format hash, I'm actually leave this out to show you something, and the length is secret. The length is 14. The last thing I need to do, this will output the data, I think, as raw or as hex, which is not what we need for this. We actually need output data format. Make sure I get this right. Out data format equals C string. And we hit enter, and this gives us two different hashes. It says you have a 128-bit check signature, which means it's MD4 or MD5. It's not MD4, we know that, so we just ignore that. It's MD5. So MD5 gives us a new signature and a new string. So we're going to take a new signature, paste it in here, take a new string, paste it in here, hit submit, and cross our fingers. Shmoocons are ready? Success. So this is a really common vulnerability to see in, for example, APIs, which assume that because you have a shared secret, that it's secure. All right. Kittens. Okay. All right, so a quick summary. If an attacker has access to the hash in the form of secret plus known data, he can trivially calculate secret plus known data plus padding plus anything. So that's pretty cool. Defense, HMAC, next topic. I'll talk about HMAC after the next section. Padding oracles. So of the three things I'm talking about, this is by far the most complicated. So hash extension attacks are pretty easy. Key reuse are very easy. Padding oracles, pretty tough. And this was kind of the reason I wanted to do this talk, is because I really want to talk about padding oracles and show everyone how they work. And hopefully, I read lots of academic papers which make them really complicated. I'm really hoping to make them simple. All right, so let's do it. First of all, an overview. As I said, this padding oracle, nothing to do with the Oracle database. This is not an attack against an algorithm, an encryption algorithm. This is not against DES, it's not against AES, it's against cipher block shading, CBC. It was originally invented, as far as I know, by Serge, you know my research skills, so who knows. But as far as I know, it was invented by Serge Vaudenet in the early 2000s, and it was called the Vaudenet attack. Another name for it, same thing. It occurs when an attacker has encrypted data. He has an encrypted string that he doesn't know the value of, and he wants to decrypt it. The data can be sent to a server. The server will decrypt the data on his behalf and tell him if it was successful or if it failed. It doesn't tell him the data, it just tells him if it was successful. So that is it. So padding. Padding oracles involve padding. Who knew? So we talked about padding in the context of hashes earlier. Hashes are padded, as I said, by 800000. Ciphers are not. Ciphers are padded differently. Ciphers are padded with a technique defined in PKCS7, Public Key Crypto Standard 7, where it says that the value of padding is equal to the number of bytes of padding. So for example, assume block size of 8, which is DES. The word hello, if you encrypted it, would have 3 bytes of padding, so it becomes 333. Hello world requires 5 bytes, so it's 55555. The word password is exactly 1 block length. And if it's exactly a block length, or ends on block boundary, then you have a full block of padding. The reason for that is pretty simple. It's because otherwise you cannot differentiate a string that's 88888888 from an empty string, because it's just padding. So that's why there's always a block of padding. There's guaranteed to be padding. So CBC mode. We talked about this very briefly earlier. Let's talk about it in more detail. So this image here you can get in Wikipedia. It's basically a visualization of how CBC works. So for cipher block shading, CBC, you get a block of plain text. That block of plain text is exclusive ORed with a previous ciphertext. So I say PN for plain text N is XORed with CN-1, so the previous ciphertext, and then encrypted. So the formula I put at the bottom here, CN equals encrypted version of PN XOR CN-1. Pretty simple. I'm just trying to notate things so we can talk about it better later. Decryption is the opposite. With decryption, you first decrypt the block of ciphertext, then you XOR it with CN-1 again, which undoes the XOR from earlier, and then that's your plain text. Simple. So we have two formulas. Ciphertext equals that, plaintext equals that. If we put them together, we can decrypt encrypted data. So reading formulas in front of a crowd is really annoying to everybody. So I'll just read briefly. So the three lines at the bottom, you're decrypting the encrypted version of all that. The D and the E cancel out because if you decrypt encrypted data, you just get the data, right? So it decrypts the block just like ECB would, and then it XORs a block with Cn-1 and XORs that with Cn-1. Now, the idea of XOR, for those who don't know, is that A XOR A equals 0. So Cn-1 XOR Cn-1 cancels out, and therefore Pn equals Pn. Plaintext equals plaintext. Proven. So, thanks for coming. A equals A. Right home. All right, so how does this work? So first, when you encrypt stuff, the person encrypting data adds padding. They encrypt each block individually, and then they send the block to the recipient. The recipient receives the block, decrypts each block, and then verifies the padding. Now, it's that verification step where you can go wrong. If the padding verifies properly, then the server accepts it. If it doesn't verify, the server rejects it. The problem is the server has to reject it silently, and that's the key here. If they don't do it silently, it's a vulnerability. So let's take an example, hello world. So P, the plaintext, equals hello world. P1 equals hello WO. P2 equals RLD. This is 8-byte blocks. 8-byte blocks. Then the padding's added. So P2 has 55555 added to the end of the text. And then each block is encrypted. The first block is encrypted to C1 by mixing with the IV. We're not going to talk about IVs for this attack at all because they just don't matter in this case. I have a blog on skullsecurity.org if you want to know more about this, IVs and everything else. So it encrypts it with the IV. It becomes 8A, EC, etc. That value is fed into the encryption of P2 and XORed with it, and that is encrypted to C2, which is 287C, blah, blah, blah. Those are put together, and that's the encrypted data. So hello world encrypts to that 16-byte sequence right there. The key I use for this is probably my des key or something. You can easily figure it out. Like I said, all these are real legitimate encryptions. All right, so now the attacker captures this string or has access to this string. What can he do with it? Well, he knows, or in theory he knows, or can figure out that this is a block cipher, block size is 8, and it's CBC mode. If he knows that, he can then take C1 and C2 individually, like that, and break each one independently. Now, in theory, he could do this in any order. He can break C1 and then C2, or C2 then C1. Because each block is broken from end to beginning, it makes sense to do everything backwards. So we're going to look at how we can break C2. So C2 is 287C, and so on. Now, as an attacker, we take this value, this encrypted data here, this 8 bytes of encrypted data. We prepend our own data to it. We're going to call that C prime. C prime can be anything we want. To make this easy to visualize, C prime is all zeros. So we have a bunch of zeros and then C2, which is 287, whatever. We send it to the server. The server tries to decrypt this. What happens? Well, the server thinks it's decrypting the real data. It thinks it's decrypting C1, C2, but it's not. It's decrypting C prime C2. What's this mean? Well, let's look at our formula for decryption. Pn equals decrypted Cn XOR Cn-1. What is Cn-1 in this case? Cn-1 is C prime. The server thinks Cn-1 is the actual data. It's not. It's my data. So it's going to XOR it with the wrong data. The other thing to note here is that there's a D in there, which means the server is decrypting for us. That's nice. It means the server is doing the decryption. We're not. All we're doing is exclusive OR. Like I said, that's all we need. So what's going to happen here at the bottom is that P prime 2, that's the decrypted version of P2, is going to be decrypted as the decrypted C2, which is the legitimately decrypted block C2 XORed with C prime. That's our fake C prime block. So what happens here? I should have numbered these. So I'm going to start about halfway, C2. So ciphertext 2, how was that calculated? So C2 was originally calculated by taking the encrypted version of P2, the second plaintext block, and C1, the real first ciphertext block. P prime 2 now is decrypting that. So what happens when we decrypt that? Well, we decrypt it, and then we XOR it with C prime. I mean, we don't. The server does this on our behalf. So the server decrypts it and XORs with C prime. On this last line here, we can now define P prime of block 2, so the second plaintext block, the second fake plaintext block, is equal to the second real plaintext block XORed with C2, which is the second ciphertext block, which we know, XORed with C prime, which is our ciphertext block, which we control. You notice there's no encryption there anymore, it's just XOR. The server just took care of all the encryption for us. We're just working with the exclusive ORs. All right, so what can we do with this? Well, we now have an equation with 4 variables. We have C prime, which we control. We have C1, which we know, that's the previous ciphertext block. We have P2, the plaintext block that we want to decrypt. And we have P prime 2, the new plaintext block, which was just decrypted. We know 2 of these. We don't know the other 2. How do we do this? What do? Well, here's the thing. We do kind of know something. We know that P prime 2, after it's decrypted by the server, is verified. If the padding on it is right, it's accepted. If the padding is wrong, it's rejected. What's the padding? What's valid padding? Well, 1 is valid padding, 2 is valid padding, 3 is valid padding, etc. What are the odds? We're going to get a single 1 or 2 2s or 3 3s. We're probably going to get a single 1. There are cases where we can get 2 2s, 3 3s, 4 4s. It can happen. It's rare. We're not going to worry about that for this case. We know that when we get valid padding, P prime 2 ends with a 1. It has to. So this slide I already most talked about. One thing to recall is that P prime 2 is mostly a garbage string. It's the system's, the Oracle's attempt to decrypt a fake block and a real block put together. So it's going to be a garbage string, except for that last byte, which is going to be a 1 because the padding is correct. So what's this mean? It means let's take a look at one block. P prime 2 of n, where n is the last byte in the block, that is going to be a 1. We know it's a 1. This C1n, the last byte of C1, we know that. That was captured. The last byte of C prime, we know that. We chose it. So now, using our formulas, we can define P2n, the last byte of plaintext, with 3 values that we know. That's math. It works. So I'm not going to go through each one. I actually wrote a blog. It's on skullscary.org. I spent about 4 hours doing a padding oracle by hand, every single byte. It was terrible. Please read it so I didn't waste my time. It turns out the last byte winds up being a 2 6. If we do the math, P prime 2 of n is 1, the valid padding. C1n is 22, the last byte of C1. If we go back about 10 slides, we'll see that. C prime n was 26 when it started working. You XOR those 3 together, you get 5. Recall that P2 ends up with 5 because it's padding. That's a padding oracle attack. That's 1 byte of padding oracle. I'm not going to do any more bytes in front of you. How am I doing for time? I am almost out of time. All right. So thankfully it's the last talk of the day, so I can go a little bit late, I was told. So that's good. So basically the idea is, by having the server tell us whether the last byte of the plaintext, which is what we called P prime in this case, was valid, we can then decrypt everything else because we can then represent that mathematically. We can just as easily do it with the second last byte, third last byte, fourth last byte, and so on. Once we decrypt 1 byte, we can decrypt the next byte. So again, I wrote a tool for this. This tool is called Poracle. All these are on my GitHub too, by the way. I'll give you a link a little bit later. So this one's a little more complicated. So here's the text. 48A3 happens to be what this encrypted to. You hit submit, and it decrypts it successfully. You change a byte at the end. You change a byte at the end, change 7 to 8. You encrypt it, it fails. Or decrypt it rather, it fails because now the padding's wrong. For this example, I use AES 256 because it's pretty secure in most ways, but not when we do it like this. So there you go. The tool for this is actually almost identical to the tool for prefixer. You basically write a module that basically tells it how to access the different fields. So I'm going to start by this page. So on this page, just like the last one, I put a string here, which has 3 square brackets and then the encrypted string. So we're going to extract that. So cd // Poracle. Copy demo to Shmoocon. Edit Shmoocon. So just like before, it includes HT party, which apparently is really cool, and Poracle. So we're going to call it class Shmoocon. We have access now to the IV, to data, and to block size. So it actually exports a few variables. We're going to rename it to Shmoocon. So in the initialize function, we need to set the data variable to the encrypted string. So that's pretty simple. I copied it already. I'm going to paste it. And then we need to parse data, which just like before is just simple as a few gsubs. Gsub slash dot star slash bracket. Can't forget the M. Do the same thing with closing brackets. And the rest should all work. The pack converts it from hex to binary. We're going to use a nil IV for this because I don't really bother with that. Our block size is 16, which is right for AES. Then we need to implement the attempt decrypt function. The attempt decrypt obviously attempts to decrypt the data and returns a Boolean, true or false. So for that, we're going to hit submit. We're going to take this URL here, try to at least, and then replace that. And we paste. All right, so result equals that. When we fail, we get the text failure. Character set, just like before, Battlestar Galactica. Create a new module, Shmoocon, and then put the decrypted version. So Poracle.decrypt, the module, the data we're decrypting, the IV, which is nil in this case, and true means verbose in this case. We save that, we run it, and once again, there you go. Decrypts from the end to the beginning, which is why it looks a little weird. All right, so no shmoo balls get thrown at me for this one. Excellent. All right, so let that go. All right, so prevention. How do you prevent this? HMAC. If you give somebody encrypted data to hold on to, verify it before you decrypt it. Yeah, almost there. Solutions. I have about -2 minutes left, so I'm going to go through this fairly quickly. I was told I can go till the end of the hour, so I have actually 8 minutes left, kind of. All right, so solution 1, don't give encrypted data to attackers. If you can avoid it, don't let them hold encrypted data. Give them an index, give them a session ID, give them something like that. One of the famous Penning Oracle attacks was against ASP.NET when you encrypted the view state or the other data on the page. If you can, why are you putting stuff in encrypted hidden fields when you have a session? Like, why? Yeah, if you let attackers hold encrypted data, you're going to have a bad time. Solution 2, when you give them encrypted data, which is bound to happen eventually, validate it. Moxie Morgenspike, as far as I know, coined the cryptographic doom principle, which says if you do any cryptographic operations before verifying a signature, before verifying the encrypted data, bad stuff will happen. So always use an HMAC. And make sure you actually use an HMAC and not like secret concatenate with data. We know why we don't do that. So alternatively, there's a mode for ciphers called EAX mode, which is actually authenticated encryption, which is what we need. Since I wrote this, there's a competition out called CSER, a competition for authenticated encryption, security, applicability, and robustness, which is apparently a competition for the next generation of validated hashes. So keep an eye on that. That can come in very handy soon. And of course, this guy. If you perform cryptographic operations before verifying the hash, you're going to have a bad time. And solution 3, the last solution, never encrypt data with the same key and same IV. Even if you validate data with a proper HMAC, with proper everything, use a good algorithm, blah, 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 if you encrypt the same key and same IV, it's going to fail. And of course, if you encrypt 2 things with the same key and same IV, I'm going to punch you in the throat. Like, seriously. Don't do that. And that is all. So. So there's my blog. I work for Leviathan Security. We do consulting work. Hit me up if you need that stuff. I'm releasing 4 tools here. The last one, Unzypher, I didn't talk about at all. It's for compression attacks. I didn't have time, so check those out. This talk will be on my GitHub. Like I said, lots more stuff. And I have one of these to give away for a good question. If anybody has a question, please ask. At the back. How did I not fail all 3 demos? I made some very specific sacrifices that I can't talk about till I'm back in my own country. Yes.
Question. You said to use randomized IVs.
Yes.
Different IVs. How do you prevent birthday attacks?
How do I, sorry?
Prevent birthday attacks? Because usually randomized IVs
Yes.
cause collision.
Okay, so the question was, with randomized IVs, how do I prevent birthday attacks? The key to that is using long IVs, long random IVs. So WEP used 24-bit IVs. 24-bit has 1.6 million or 60 million different values, which collides every 5,000 guesses or so. That's bad. If you use a 32-bit, 64-bit, 256-bit IV, you're not going to get collisions because of birthday paradox in this lifetime. It's just not going to happen. So just use good IVs, use long IVs. Yes?
In Cutting Oracle, we were using clear text data, for example. But if you have a binary data which is exactly the same what your pad is doing, let's say like then Cutting Oracle will that work or not?
Okay, the question was, all my examples use plain text data. Will the same thing work with binary data, where the data is indistinguishable from hashing, or from the padding rather? And the answer is yes, it'll work just fine. It turns out the padding is predictable because the padding is always at the end and always has a value of 1 or 2, 2 or 3, 3, 3, which means we can easily distinguish it from real data. So yes, it'll still work, and it'll work fine. Yeah. All right, I guess that's it. So thanks everybody, and yeah. Pardon?
Ron, please give Ron a warm welcome. Crypto, you're doing it wrong. For guys that are standing on the outside, there are a whole bunch of chairs up front. Come over here and sit down, make some friends. You don't have to stand for the whole talk. You can come sit down. Most of the people at Shmoocon shower. This is not like Vegas. All right, I guess the rest of you want to stand the rest for the next hour. Anyway, come sit down. Make a friend. All right. With that, I'm actually going to hand it over to Ron, so good luck.
All right, thanks everyone. So before this talk, I was at the bar at the hotel. Apparently next door, there's a conference about pornography and voyeurism and stuff. So thank you so much for coming. Like, seriously. I thought of skipping. Like, microphone. Is it on? Closer to my mouth? Move it closer to your face. I hear that a lot. All right. So let's get going. So my name obviously is Ron Bose. On Twitter, I'm YagoXA6. I have a blog, Skull Security. I work for Leviathan. We founded Skull Space, Winnipeg's first and only hackerspace. Apparently they're watching on the live stream right now, and they're taunting me from IRC, which I can't see, thankfully. And when I'm not doing computer stuff, I'm in the rock climbing. Yes. I live on the prairies, so it's interesting. All right, so my agenda for today, I'm going to start by talking about the history of crypto attacks a little bit. I'm going to do some examples, try to make it funny. The last part is LOL, in case you couldn't guess. So after Caesar, there was a couple thousand years of developments and stuff like that. I decided to be really lazy and do the research, so I went to 4chan. And I asked them for chat if anything happened in the interim between Caesar and Enigma, and they said no. So, so, as you can imagine, it was quite a time saver. All right, so Enigma. I promised my friend I'd put Hitler in the talk somewhere, so here he is. He's been Goodwind, Godwind, whatever. All right, so the Enigma machine was the first real crypto that I know of that was actually more difficult to break than just like making guesses until it worked. To break Enigma, it actually relied on things called cribs. And if you guys want to learn a lot more about this, Wikipedia was great. I spent a whole day when I was supposed to be working reading Wikipedia. I also, the Cryptonomicon is an amazing book. They talk about this in great detail. Neil Stephenson, I highly recommend that book if you haven't read it. But anyway, the idea behind Enigma is that they had to break it at the time. They had to know certain keywords that were in messages. And if they could break a message for the day, any single message for a given day, they can break all the messages because of key reuse. So that was really cool. But how do you break one message? Well, they had to figure out some content that was in the message. And they had a lot of ways of doing this. I'll talk about 3, and then I'm going to move on to actual modern attacks. So one way, the Germans actually had a whole bunch of spies in the UK, and the UK knew about them because Enigma was broken. And at points during the war, MI5, the British intelligence, could say, we're 100% certain there are no unknown spies in the UK. Every spy is either... I had a really ambitious talk planned out. It was about 3 hours long, so I cut out a bunch of stuff. I'm posting some slides to GitHub after. It's going to have a lot more slides than I actually present. It's going to have, I think, 2 more vulnerabilities and 1 more tool that I don't even talk about today. So make sure you check my slides after. There'll be a lot more. So I have three major types of attacks I'm going to talk about, and each of them I have a demo, and the demo is going to be live coded on stage. I arm my friend with a Shmoocon. If I script a demo, he's throwing it at me. So they'll give you right the first time, I promise. But then I'm going to talk about some solutions, because when I don't talk about solutions, people get mad. So why am I doing this? This actually originated with a Capture the Flag contest I did a few months ago. It was Stripe CTF. There was a level in it where you had to implement a padding oracle, a hash extension attack, and it was tough. Like, I've spent like 6 hours till 8 o'clock in the morning working on this before I finally got it. And I decided to write a tool for it. And after writing that tool, I wanted to write more tools for some other attacks, like padding oracles and stuff like that, just for my personal interest to learn how they work. And then suddenly I had a bunch of tools and a bunch of cool, not new research, but stuff that people have done before, but that hasn't been presented really well that I could find. So I thought I'd do a talk about it, and here I am. So, history of crypto. So this is going to be a very brief history. It's not going to be very accurate, I promise. So it all started in 75 BC or so with Caesar. Caesar allegedly had what he called the Caesar cipher, a shift cipher. It had 25 possible encodings, 26 if you count A becomes A, which is a terrible encoding. Yeah, it's double ROT 13. It's secure. It's twice as secure as ROT 13. And I actually did, as research for this, I did a crypto quote, and it took me about 10 minutes. I took a video of it. I can show you the video if I run out of time, or if I have extra time. It's terrible. I won't show you it, I promise. But it's trivial to brute force. And this stuff you see on the screen, and all examples I give are all legitimate encoded stuff. You can verify it. You can look it up. I optimized and would verify anybody. You know, there's lots of talks about bad CAs. I'm not going to talk about how bad they are. They're just, you know, we all know they're bad. While we're talking about goat seed, let's talk about WEP. So WEP uses RC4, which is, it can be used securely still. It's very difficult to, but used with a 24-bit IV. And we're going to talk about IVs and how important they are later. But for the purpose of this, a 24-bit IV is totally worthless. You get a collision every 5,000 packets or so, which is, you know, as soon as you have 2 packets of the same IV, you have a problem. So, you know, RC4, an okay-ish cipher. How it was used, not so good. GitHub. So this is a story from a couple weeks ago that was actually pretty interesting. You know, it kind of goes well with my talk because GitHub and other GitHub is giving people, GitHub and SVN and stuff, they give people a great place to accidentally post keys and accidentally post passwords. And that happens a lot. Like, who here hasn't posted a password to GitHub by accident at one time or another? You know I have. So, you know, what's the point of all this? Well, the point is that encryption is rarely broken directly anymore. Most of the algorithms we have, you know, even things like SHA-1 and MD5, they're bad algorithms. They have a lot of attacks. But it's rare that you actually break something through directly attacking the algorithm. It's broken by bad implementations, by developers, bad operations by end users, just stupidity like CAs, various side channel attacks, timing attacks. The Lucky 13 or whatever it is, vulnerability from last week, I think, was a timing side channel attack against SSL and TLS. Like, we're not breaking the algorithms directly. We're breaking them through side channels, and that's kind of the point of this whole intro section, and the point of the next three examples I'm going to give. We're not going to break anything directly. We're going to break them by how they're implemented and how they're used incorrectly. So arrested, deported, or working for us. And it was true. There was no German spies in the UK for long periods of the war. So the spies that were on the British side, the turncoats or whatever, they would send messages that had special keywords in it, and those messages would get repeated over the secure Enigma network. And those keywords could be found by the cryptanalysts, whatever, the smart people. And they would use those to decode the messages, and that would let them decode all the messages for the day. In the Cryptonomicon, they talk about this. They would plant mines at certain locations, and they knew how the Germans would encode the locations as coordinates and send them on Enigma. So they would find these coded strings, and then use those to decrypt that message, and therefore all the messages. Like, it's really cool. And a lot of this comes down to operator error, like the fact that the Germans should have known better than to leave code books lying around in some cases, or to start every message with a current date, or things like that. But they didn't, and that let them be broken. So that's kind of where I'm going with this. So more modern. That's not very modern. All right, so DES. So in the 1970s, we got DES, a symmetric key cipher. Basically, messages can be encrypted by a person and decrypted by anybody with a key, which is the recipient and everyone who's stolen it. So that's obviously a problem. Key management, right? It's always a problem. Which leads to asymmetric key encryption. Diffie-Hellman, RSA, stuff like that. For asymmetric encryption, both parties, Alice and Bob, have to exchange their keys with either each other or with Eve, and then they can communicate with each other through the untrusted third party. So again, this is a problem, implementation problem, which leads to CAs. I promise I finally put Ghosty in my talk. That's the best I'm going to give him. Sorry, Mac. So basically, with CAs, you could try to verify certificates from people, and whichever CA was the most trustworthy, or was the least trustworthy, would be